This is the first video that goes over all of the questions from the 2015 released SOL for chemistry. This might be one of the best resources to use in order to pass the SOL and get a verified credit and also some extra bonus points in your grade. This is a percent error question, so as a quick review before you even talk about the question in particular, percent error is equal to the absolute difference between the experimental value and the true value, all divided by the true value times 100%, or times 100 to get a percent. So in this problem it says a student measures the mass of a 1 gram aluminum rod as 0.99 grams. 0.99 is his experimental value that a person gets using an instrument, and 1 gram in this case is the true or actual value for the mass. So according to this, the experimental value, 0.99, minus the true value, which is 1.00, the absolute difference can't be negative, divided by the true value, which is 1.00, times 100, you get 0.01 divided by 1 times 100, and that gives you a 1% error. The chance of you having a percent error question is pretty high. It won't be necessarily as simple as this. Some other percent error questions actually ask you to calculate the experimental measurement. For example, if you are given the true density, the true value density of something as 2.5 grams per milliliter, they may ask you to determine what the experimental value density is if they give you the grams or the mass of the substance, and then they give you the volume of the substance. So in one of those more complex percent error problems, you need to calculate what the density is, for example, and that would be your experimental value density. If it says a student calculates the mass of a pebble and the volume of a pebble to be this, you need to find out what is the density of the pebble that the student would have calculated. And if this is the actual density of the pebble, then you would then use the experimental value and the true value to determine the percent error. So this one is an easier percent error problem. Just recognize that there are ones where you have to do a little bit more work. The most efficient way to determine whether a reaction is exothermic or endothermic is to use, this one really asks you two different things. It's a little bit about instrument, but it's easy to estimate what the instrument could be if you understand what exothermic means. So terminology is important. Exothermic means that the system releases energy, usually in the form of heat. And heat can be measured using a thermometer. And the word thermometer is not on here. But temperature probe would be the next best option, because temperature probes measure temperature, just like oxygen probes measure oxygen, and pressure probes measure pressure, and pH probes measure pH for acids and bases. So if something is releasing energy, the way that you can determine if it's exothermic is to see if there's an increase in temperature. Recall that exothermic and endothermic reactions tend to look, as far as reaction energy diagrams, like this. That was not a very good smooth curve, but you get the idea. This would be an example of exothermic, negative delta H. And this would be an example of endothermic, a positive delta H. And this release in energy will be felt as a temperature increase. Which type of chemical reaction does this equation represent? We talked about all sorts of chemical reactions, synthesis, decomposition, all those different ones. So a synthesis reaction is when you have two simpler substances coming together to create a more complex substance, such as a compound. You could have two compounds coming together to create a more complex compound, but a synthesis reaction will have two or more reactants and then a more complex single product. Decomposition reactions are the opposite. A decomposition reaction will have something that is more complex, like a compound, and it decomposes into the simpler substances that make it up. Two or more substances. Could be elements, could be simpler compounds. So synthesis and decomposition are pretty straightforward. Then you also have single replacement or single displacement. A single replacement reaction happens when you have a single, often a pure element, and a compound, and then on the other side you get a different pure element and then a new compound. So remember that with single replacement reactions, something in the compound gets kicked out, so to speak, and is replaced. Double replacement. Double replacement reaction is just more complex. You have two compounds that react to give you two new compounds. These often can occur with metals or acids and bases, and they are the most complex looking reactions as long as they're not neutralization. A neutralization reaction involves an acid and a base that create water and a salt. So let's take a look at this example, or this particular problem. You have a metal cation and a nonmetal anion in one compound. You have a metal cation and a nonmetal anion in the second compound. On the other side, you get a metal and a nonmetal, and a metal and a nonmetal. So you get two new compounds. The positive and negative charges have switched places. Aluminum acetate and barium sulfate create aluminum sulfate and barium acetate. This would be an example of a double replacement reaction, because you have an AB and a CD creating two new compounds. What is the oxidation number of an oxide ion? This one is about terminology as well. Oxidation number you can think of as the fancy word for an electric charge on a species, or in particular on an ion. So oxygen, if you're looking at just the P block, oxygen's in this family above sulfur and selenium, and you've got fluorine, which is above chlorine and bromine, and then you've got the noble gases over here. The noble gases tend to have an oxidation state of 0. The halogens tend to have an oxidation state of -1, and the oxide family tends to have an oxidation state of -2. So think about the fact that if you had a compound called sodium oxide, what would the formula be? In order to get the formula, you would look at the sodium, and remember that sodium is Na+, so sodium has an oxidation state of +1 as an ion. Oxide, it's one of those ones you just have to remember, has an oxidation state of -2, being in this family. So if you do the switchy trick, you would get a final formula of Na2O. That's just a reminder of how oxidation states work in naming, but for this particular example, the oxidation state of the oxide ion is simply 2- or -2. Both would be accepted. Now put yourself in the shoes of like a test maker. They may not say oxide, they may say fluoride, or they may give you a particular compound such as potassium nitrate, and they would ask you to determine the oxidation state of the potassium ion. Even though it sounds like a scarier problem, potassium is going to be +1, and the nitrate collectively is -1. This problem is, what is the molarity of a solution with 0.2 moles of potassium permanganate dissolved in enough water to make a 500 milliliter solution? So this is a molarity problem. One of the most important equations to remember is molarity, which is basically the concentration of a solute in a solution, is equal to the moles of the solute, which, by the way, in this case is potassium permanganate, divided by the liters of the entire solution. So let's see if we can pick out some pieces. We are finding the molarity, so we don't know the molarity. We are given the number of moles of potassium permanganate, that is 0.2. And we have the volume of the solution. But look carefully at the volume of the solution. The volume of the solution is 500 milliliters, but the molarity equation must be written in moles per liter. So 500 milliliters is not 500,000 liters. One of the biggest mistakes is people going the wrong way when they convert milliliters to liters or vice versa. So remember that 500 milliliters will be 500 milliliters over 1. Turn your milliliters into liters. 1 liter has 1,000 itty bitty milliliters in it, and what you get is 0.5 liters. And that gives you your molarity. 0.2 divided by 0.5 is 0.4, capital M for molarity. So the answer would be 0.4. This problem is when 92 grams of ethanol are vaporized at its boiling point of 78.3 degrees Celsius, it requires 78.6 kilojoules of energy. What is the approximate molar heat of vaporization of ethanol in kilojoules per mole? This is one of those problems where people will look at it and they'll be like, I have no idea what's going on. But one of the easiest things to do when you have no idea what to do is two things. And this is very important to understand. The first thing is recognize that the mole is the goal. And if you don't know what to do, take a mass and turn it into moles. I have 92 grams of ethanol. I know that my amount is given to me right now in grams, and then I know that grams and moles are very easy to connect. And I see moles right here. So I'm going to turn my grams into moles because I'm sitting in the testing center and have no idea what to do. So I'm going to turn those 92.0 grams of ethanol, C2H5OH, into moles. Because I can at least do that. The molar mass of ethanol, I'm going to ask Google to save some time. Actually, I'll just figure it out real quick. The molar mass of ethanol is about 24 for the two carbons, plus 6 for the oxygen, or for the hydrogens, plus 16. So it's about 46. So 46 grams per mole. The number actually works out really nicely. 92 divided by 46 is just 2. So I know that I have 2 moles of ethanol. Once you have your moles, because that's the goal, you need to see if a relationship pops up. 1 mole when vaporized, 92 grams of ethanol when vaporized requires this many moles. So I'm going to set up a proportion just to see if anything occurs to me, a direct proportion. It looks like I have kilojoules and moles. Always look at your units. So kilojoules and then moles, kilojoules and then moles. Remember that direct proportions require the same units on opposite sides and in the same positions of the equal sign. From my problem, I know that 2 moles of ethanol required 78 kilojoules to vaporize it. But I'm asked for the approximate molar heat of vaporization in kilojoules per mole. From the problem, I know that I'm going to need 1 mole on the bottom because I want to know, well, how much energy does it take to vaporize just 1 mole of ethanol? 1 mole of ethanol will require half of 78.6, which is 39.3. And the units would be kilojoules per mole. So there's a couple of things to do if you're completely lost and you don't feel like working out through all the logic of the heating curve and such. One of them is turn your mass into moles and see if a direct proportion pops up. Looking at this temperature, we're not using this temperature because it says it's vaporized at its boiling point. This is the boiling point of ethanol. It is completely irrelevant to the math of the problem. Because if you remember about heating curves, the heating curve has 5 sections. Section 1 is the solid, section 3 is the liquid, section 5 is the gas, section 2 is fusion, which is when the solid is turning to a liquid. Section 3 is vaporization, which is when the liquid is turning to a gas. We are vaporizing ethanol in this example. And while it's vaporizing, the temperature is constant. Matter of fact, during any phase change, the temperature is constant. If the temperature is constant, then there is no change in temperature as you add heat. So you cannot use Q equals mc delta T because there is no change in temperature during a phase change. A lot of people will want to somehow use this number because they see this number and they think I have to use it mathematically, but you don't. So when you can't use Q equals mc delta T because there is a phase change and no temperature change, then you have to just set up a proportion. This is the last example we're going to do for this video, and then the next one we'll pick up after this. What is the density of an aqueous solution that has a mass of 10.081 grams and 12.5 milliliters? So density, as a review of middle school science, density is the mass in grams divided by the volume in milliliters or cubic centimeters. For standard density problems, you're going to have grams for your mass and milliliters for your volume. For gases, you will have liters for your volume, but milliliters and cubic centimeters are going to be common for standard things. So density is grams per milliliter. See what we can fill in. We have 10.081 grams divided by 12.5 milliliters. So I'm putting into my calculator 10.081 divided by 12.5 gives me a string of numbers that is 0.80648. You're going to be tempted to just calculator dump that number into that box. But look very carefully. It says your answer must use significant digits or significant figures, same thing. How many significant figures are in 10.081? The answer is 5 sig figs. How many are in 12.5? The answer is 3 sig figs. But when we do our math in the calculator, we get 5 sig figs. And if you remember from significant figures, we cannot use or report more digits than the lowest number of sig figs in the problem. So between 5 and 3, 3 is the lowest number of sig figs. So we're going to have to cut our answer off, providing only 3 sig figs. So the answer you put in would be 0.806. If you were to put in more digits, you would actually get the answer wrong because this is less of a problem of testing if you remember the density equation, and more of a problem to see if you remember and learned what significant figures or significant digits are.